example where we can show these strains and actually represent some of the terms for strain individually. So this is an example of how to deconvolute a set of strains. We're going to take the same set of axes as used in the prior example and see if we can define things. So we have x and y, and the first thing that we've done is we've just taken what was initially a shape that was defined by this square here, right, and we've stretched it along the x-axis, and we can describe that strain as a normal strain or as a strain E that includes rotation, since there is no rotation for the normal strains. So we know that E11 is always equal to epsilon 11. And approximately, we should say approximately for this case, approximately this strain will be, we'll put an approximately symbol on there, is E11 is equal to 3 divided by 5 is equal to 0.6. So we could describe that strain as an approximation there for that relatively large strain. And we could take this one step further and describe it so that we actually, after doing this initial deformation to produce this shape, we subsequently strained material this way, adding essentially 2 blocks to what was initially 5 blocks. So it's 2/5 equal to approximately 0.4, and we could describe the total strain tensor as something like this. If we were to calculate these in terms of true strain, right, so we would actually solve for the true strain, we get 0.47, 0.34, and 0. Okay? And we can, for any of these examples, we could calculate these as true strain. So how do we take this and shear it? So we're going to take it and we're actually going to undergo a simple shear and show that in the next frame. So we're going to take this simple shear and we're going to extend this initial rectangular object over so that it is simple sheared along this way, and we're going to keep the area just about the same. And in this case, if we describe this as the dimensional change that's taking place here, right, we've actually shifted this over as a simple shear, and we haven't really changed this point at all. We've kept this the same, but it's undergone a displacement in the u direction of a component y, something like that. So we get a strain E12. Okay, so that's the first strain that we can undergo here. And then if we actually rotate this up to here, right, we could actually just have it undergo a strain, take that initial object and have it go a rigid body rotation, right? A rigid body rotation of minus 0.7 and 0.7. So we took this object from here and we rotated it up to here. Just a straightforward rotation, equal and opposite terms here. And by the way, there is a 0 missing in this particular example. And we end up with what started out as this initial square, now rotated up into this object. And if these terms are additive, if we can actually add these components together, then we can sum them, realizing that it would be better to do each of these strains in increments and to keep track of things in terms of true strain. But we can get to the following result, which is shown here, so that the total strain is described here as the sum of the rotation plus the deformation to give the total. And that will be the approximate solution for the distortion from the initial square to the final object. Let's do one example to make sure we have the subscripts defined well, and we'll do that example in the next frame. shown here. So let's define a set of axes. That's always the first thing. Since it's arbitrary, we're going to make our choice to define it. This is x, y, and z, which is the same thing as 1, 2, and 3, and you'll see both conventions in different places. And let's have this undergo the strain E2, 3, right? So from our axes, right, this is x, this is y, and this is z. And so we're going to have a strain that's a shear strain which has a displacement in the two direction of an element along 3. So that should be a strain that looks something like the following, depending of course on the magnitude. And we should get a final object of a shape similar to that. So thank you very much, and I hope this helps your understanding of strain.